Have you ever wondered what happens when a massive star reaches the end of its life? We often hear about black holes and neutron stars, the cosmic remnants of stellar deaths. But what if I told you there's a new frontier in astronomy that could soon allow us to detect these catastrophic events in real time? Today, we're diving into a groundbreaking development that could change how we understand the universe: the detection of collapsing stars through gravitational waves. To truly appreciate this discovery, let's start with the basics. When stars exhaust their nuclear fuel, they face one of two fates. For stars with a mass up to 8 times that of our Sun, the end is relatively calm, resulting in a white dwarf. However, for more massive stars, those with a mass greater than about 8 times that of the Sun, the end is far more violent. These stars explode as supernovae, leaving behind either a neutron star or a black hole. Now, neutron stars and black holes are some of the densest objects in the universe. A neutron star is what's left when a star's core collapses, squeezing protons and electrons together to form neutrons. This process creates an object with the mass of about 1.4 times that of the Sun, all packed into a sphere just about 10 to 20 kilometers in diameter. Imagine compressing the entire mass of the Sun into a city-sized object. That's a neutron star. Black holes, on the other hand, are born from the collapse of even more massive stars. Here, gravity overwhelms all other forces, compressing the core to a point of infinite density, a singularity where the known laws of physics break down. Surrounding this singularity is the event horizon, the point of no return beyond which not even light can escape. For decades, these stellar corpses have fascinated scientists, but detecting them has been a monumental challenge. That is until the advent of gravitational wave astronomy. Gravitational waves were first predicted by Albert Einstein in 1915 as part of his general theory of relativity. These waves are ripples in the fabric of space-time, generated by the acceleration of massive objects. Think of them as the cosmic equivalent of the waves generated when a stone is thrown into a pond. However, instead of water, these waves propagate through space-time itself, traveling at the speed of light. The idea of detecting gravitational waves seemed almost impossible until 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. LIGO detected the gravitational waves produced by the merger of 2 black holes, a discovery that opened a new window into the universe. Since then, LIGO, along with its European counterpart Virgo, and the Japanese detector, KAGRA, has detected numerous events involving the mergers of black holes and neutron stars. These detections have provided unprecedented insights into the nature of these enigmatic objects. But what if gravitational waves could reveal even more? What if, instead of just detecting the aftermath of these cosmic collisions, we could observe the very moment when a massive star collapses to form a neutron star or a black hole? This is precisely what a team of researchers led by Ore Gottlieb has proposed in a recent study published in the astrophysical journal Letters. Their research suggests that gravitational wave observatories could potentially detect the collapse of rapidly spinning massive stars before they become black holes. Let's take a closer look at what happens during a stellar collapse. When a massive star, say, one with a mass between 15 to 20 times that of the Sun, exhausts its nuclear fuel, its core can no longer support itself against the force of gravity. The core begins to collapse, and within a matter of seconds, it can shrink from thousands of kilometers across to just a few kilometers. This rapid collapse generates an enormous amount of energy, some of which is released in the form of gravitational waves. The study by Gottlieb and his team focuses on stars that are rapidly spinning at the time of their collapse. In these cases, the collapsing core forms a disk of material around the nascent black hole or neutron star. As this disk spirals inwards, it can generate gravitational waves strong enough to be detected from Earth, even from a distance of up to 50 million light-years. To put that into perspective, 50 million light-years covers a vast region of our cosmic neighborhood, including galaxies like the Andromeda Galaxy and the Virgo cluster. What makes this discovery particularly exciting is that it opens up the possibility of detecting a whole new class of gravitational wave events. Until now, gravitational wave observatories have only detected the mergers of compact objects, black holes, and neutron stars. These events are incredibly powerful, but they are just the tip of the iceberg. The collapse of a massive star, while less energetic than a merger, could produce gravitational waves with a unique signature. Detecting these waves would provide astronomers with a direct glimpse into the final moments of a star's life and offer new insights into the processes that lead to the formation of black holes and neutron stars. But the story doesn't end there. The researchers also suggest that there could be existing data from gravitational wave observatories that already contain signals from such collapsing stars. The challenge, however, is identifying these signals amidst the background noise of the universe. Gravitational wave data is incredibly complex, filled with a cacophony of signals from various cosmic events. Distinguishing a collapse event from this noise is like finding a needle in a haystack. To tackle this challenge, astronomers are now searching through existing data, looking for gravitational wave signals that might correspond to known supernova events. Supernovae are the explosive deaths of massive stars, and they are often observed in visible light by telescopes around the world. If a gravitational wave signal were detected at the same time as a supernova, it could be a smoking gun, indicating that the signal was produced by the collapse of the star's core. The process of searching for these signals is painstaking and requires advanced computational techniques. Simulations of stellar collapse events are being used to generate theoretical models of the gravitational waves they might produce. By comparing these models to real data, astronomers hope to identify potential collapse events. However, the task is daunting. Fully modeling a single collapse event requires running complex simulations that take into account factors like magnetic fields, cooling rates, and the star's rotation. To fully explore the range of possible collapse scenarios, millions of simulations would need to be run, a feat that would require enormous computational resources and significant funding. Despite these challenges, the potential rewards are immense. Detecting gravitational waves from a collapsing star would provide direct evidence for some of the most dramatic processes in the universe. It would allow scientists to study the physics of stellar collapse in unprecedented detail, shedding light on how black holes and neutron stars form. Moreover, it could provide new insights into the behavior of matter under extreme conditions, helping to answer fundamental questions about the nature of gravity, nuclear physics, and even the early universe. So what does the future hold for gravitational wave astronomy? The next generation of observatories, such as the Einstein telescope in Europe and the Cosmic Explorer in the United States, will be even more sensitive than LIGO and Virgo. These advanced detectors will be capable of probing deeper into the cosmos, potentially detecting gravitational waves from events that are currently beyond our reach. They could also provide more detailed data on the events we can already detect, allowing us to study them with greater precision. But perhaps the most exciting prospect is the possibility of discovering entirely new phenomena. Gravitational wave astronomy is still in its infancy, and every new detection brings with it the potential for surprises. Just as the first detection of gravitational waves in 2015 revolutionized our understanding of the universe, the discovery of gravitational waves from collapsing stars could open up a whole new chapter in astrophysics. Imagine being able to watch in real time as a star collapses into a black hole or a neutron star, all through the ripples it sends across the fabric of space-time. This is no longer the stuff of science fiction. It's a real possibility that could become a reality in the coming years. As we stand on the brink of this new era in astronomy, one thing is certain: the universe still holds many secrets, and we are only just beginning to uncover them. Gravitational waves are not just a new way of observing the cosmos. They are a key that could unlock some of the deepest mysteries of existence. So, stay tuned, because the next big discovery might just be right around the corner. What do you think? Could gravitational waves from collapsing stars be the next big breakthrough in astrophysics? How might these discoveries change our understanding of the universe? Let us know your thoughts in the comments below. And if you're as fascinated by the cosmos as we are, don't forget to like and subscribe for more deep dives into the wonders of the universe. Until next time, keep looking up.